All right, in this worked example, we're taking a look at state Kirchhoff's law. Let me get my microphone going now. Microphone check 1, 2, 1, 2, 3. There we go. State Kirchhoff's second law. You should have said something like the sum of the EMFs equals the sum of the potential differences. Okay. There is a certain quantity that is conserved that we could link this law to, and that quantity is mass energy, right? Because mass energy is conserved, mass energy is neither created nor destroyed, then the energy per charge, which is voltage, that we put into the circuit, right? So the EMF, that converts other forms into electrical energy. So that other forms into electrical energy per charge is equal to converting those that electrical energy into other forms, right? And that's what the PD is, right? So at each one of these resistors, right, there's a potential difference, there's a voltage drop, and the sum of those potential differences is equal to the sum of the EMFs. Here we do see a circuit where there's more than one source of EMF, right? So we sum them both. You may recall doing an example problem where we saw that if the polarity of the EMF is such that positive runs into positive, we got to subtract, right? That's not the case here, right? The positive is running into negative, and so the rule would be to add those EMF sources. But in order to solve, for example, for like the intensity of the current here, which is what the question has you do, we really have to examine a part of the circuit where we only have that unknown. If we look at this part of the circuit, we don't know the value of this resistor. We're going to eventually calculate it, right? But only once we know the value of I. So we can really hone in on the fact that this part of the circuit right here, they tell us that the voltage in this voltmeter is 0. So we think about this law, it's like saying, okay, we put some EMF into the circuit, and now the voltage drop across that whole branch is 0. Likewise, it's 0 across this part too, right? Like we could think about this as being wired across this part of the circuit or across this part of the circuit, right? But if we say, well, here, the sum of the EMFs, 6 volts, equals the sum of the potential differences. And usually we can sometimes word this, like capital E for EMF, capital V for PD, right? They're both voltages. And so here we know from Ohm's law, V equals IR, that there's going to be a current driven through here, I, times the 4 ohms of resistance. And because this voltmeter reads 0, we know that those got to be equal to each other, right? So we adjust the resistance in this variable resistor until this reads 0. And then we can solve that the intensity of the current must be 1.5 amps. Okay. A moment ago, I said that the quantity that is conserved, that is linked to this of Kirchhoff's laws, was energy. But in the future, you may see a question paper that looks like this, and it will say, state Kirchhoff's first law. And then it goes on to read, Kirchhoff's first law is linked to the conservation of a certain quantity. State this quantity. Charge should have been what everybody said after that. Settle down. I know it's funny.
Discover card here to explain our cashback match. We match all of the cashback you earn at the end of your first year.
Great. Now that's going to be on my YouTube video. Oh, well. Yeah, I'm going to get a copyright claim. No, I think they'll be okay with it. No, you can put our ad on there. This one also has internal resistance, right? So this symbol right here, you see there's like a resistor kind of in this little dashed box near the EMF source. They tell you the internal resistance is 2 ohms. And the question we're doing, there's negligible internal resistance. Lowercase r for internal resistance. We're not dealing with that in this problem because it's negligible, but you can see the example I just showed you. Sometimes we do have to deal with that. So let's now use this Kirchhoff's second law, which remember the sum of the EMFs equal the sum of the potential differences. And let's apply that to the entire circuit, like this outside loop here. Okay, so it's like one series circuit. We know that the current is 1.5 amps, and that's the same everywhere, right, in this series circuit. The sum of the EMFs, you should realize, is 6 plus 6. The rule to keep in mind is that when the positive terminal right here runs into the negative terminal here, the rule is to add those EMF sources, right? If the positive terminal were here, then we would subtract them and there would be 0 volts, right? Because 6 minus 6 would be 0. So it would be pointless to sort of wire this up. The opposite would just cancel out the energy per charge there. All right, what's the sum of the potential differences? We could start maybe with this one. So we already know like there's V equals IR, right? So we're going to sum a bunch of potential differences. If you want to think about it like this, like voltage drop 1 plus voltage drop 2 plus voltage drop 3, like there's 3 places where the volts sort of drop. All the 12 volts that we put in are going to drop across all 3 of these, but by how much? So 12 volts, let's go ahead and add that. And then let's expand this V with Ohm's law, V equals IR. So we've got the 1.5 amps of current I going through the 4 ohm resistor. So there's a voltage drop there. We're going to add, right? That's what this symbol means, sum. .5 amps times these 1.5 ohms of resistance, right, to give us a certain voltage drop across this one. And finally, we've got 1.5 amps going through this variable resistor R. A variable resistor is like a dimmer switch, okay? That's a helpful way to think about what a variable resistor is. When you adjust a dimmer switch, you're increasing, sort of resistance, and then the light gets more dim. When you turn the dial the other way, you're decreasing the amount of resistance in that circuit, so the light gets brighter. So a variable resistor is just a convenient way to adjust the resistance and therefore the amount of charge that's flowing through the circuit, conveniently. Do some mathematics with that over there, right? 12. We know that the units are going to be ohms of resistance, right? So we got amps of current, ohms of resistance, volts of voltage. So everything is the SI units. 4 times 1.5 is 6. 1.5 times 1.5 is 2.25 plus 1.5 R. 12 minus 8.25 over 1.5 R. So R equals 2.5. Right, everybody follow that? So a statement of Kirchhoff's second law in part A is going to be helpful in doing those calculations later. But they ask you about Kirchhoff's second law for a reason. So always use that as a clue in paper 2. Whatever they ask you about in part A will be helpful in part B, C, D, E, F, and so on. All right, so we took care of solving for the current and the resistance R. Now we're going to calculate the ratio, determine the ratio of the average drift speed of the free electrons in X compared to the free electrons in Y. So we had 2 resistors, we got 3 resistors, but 2 fixed resistors, X and Y, and their resistances are 4 and 1.5 ohms respectively. And we want to calculate the ratio of the drift speed of the electrons in those resistors. All right, so if you needed any of this working for a moment or 2 longer, if you had any questions about it, go ahead and leave it in the comments below, or you can just pause the video and take it down at your leisure. You may recall from a week or so ago, we derived an equation that looks like this, where V is the drift speed. So we can rewrite this as the drift speed is equal to I over NAE. That equation is necessary to be able to calculate this ratio. Like we're going to compare the drift speeds. So we're really comparing these sort of quantities. Okay, we can set it up like this. The drift speed of X compared to the drift speed at Y will be equal to, the only difference here is that the diameter of X is twice the diameter of Y. Okay, so the question is really like, if the area is pi r squared, and we double the diameter, it's like doubling the radius. What's happening to the area if we double the radius? Well, we double squared the area, okay, because the radius is squared to calculate area. So for X, we've got the current I over N, and the A, the area, is 4 times the area of Y, because we're doubling the radius, right? So we got to double square the area. So it's 4 times the area, and E is just elementary charge. So this expression compares the drift speed of the electrons through resistor X for the drift speed of the electrons in resistor Y. This one is just I over N. And then when the diameter is D, the area is A. When the diameter is 2D, right, the area is 4A. And so the only difference is that 4 right there. And so this all simplifies down to, right, the denominator, numerator, combine the numerator. The denominator here and the numerator here, combining the denominator down here. So we've got this I from there, then we got an N, then we got a 4A, then we got an E. And I like to kind of line it up like that so I can see, yep, I's cancel, N's cancel, A's cancel, E's cancel, and I've just got a ratio of 1 to 4. So the electrons go a fourth as fast through X as they do through Y. You may recall that the resistance at X was greater than the resistance at Y. And so it makes sense that the electrons would go more slowly. Resist the flow of charge more. And finally, we've got the resistance R of the variable resistor is now increased. We want to state and explain the effect of the increase in R on the power transformed by each of the batteries. So we could think about it with our intuition, with our instinct, and keeping in mind that the resistance of R, this is a variable resistor, right? And so if you increase the resistance in a variable resistor, you are dimming the dimmer switch. You're making it more dim. What does your instinct tell you about the power that's transformed in your EMF source if you make the light bulb more dim? Less power, right? You can just use that, you know, it's not a trick question. So like, okay, if it's dimmer, you need less energy, less rate of energy transformed, less power. And that works here. Don't, you know, overthink it. So, well, it's got to fight harder through more resistance and so more power. No, it's just like less power because it's more dim. Now, that might be a good way to just get to the statement of it, but it's not really the explanation we want. We want to say things like, we're increasing the total circuit resistance. Okay, so when we increase the variable resistor, there's more resistance in the entire circuit. Remember how we add resistors in series. So we're just adding our resistor X that we've considered up here, our resistor Y, and this variable resistor. So as we add more resistance, the circuit resistance, the combined resistance in the entire series circuit is going up. Okay, if we then say, well, we've got a fixed voltage, I equals V over R. If we're increasing this, okay, we're making the denominator bigger and bigger and bigger here, then the current is going to do what? Go down, right? If the resistance goes up, then the current that we're drawing from the EMF source is going down. Okay, so the explanation, we have to connect those ideas. Increasing the variable resistor increases the circuit resistance. Okay, and an increase in circuit resistance means we're going to draw less current from the EMF source, from the batteries. So what's that going to do to the power transform? Well, you may recall that power is calculated as I squared R, or I times V, right? So, or V squared over R. So a decrease in current is going to mean less power is transformed. Okay, a decrease in power due to the decrease in the intensity of the current. That's closer to an explanation as to sort of why that's true. But again, it's sometimes helpful to just think about it like a dimmer switch and, you know, like let your intuition kind of guide your thinking more. So please don't just put these bits of equations on your paper and let that stand as an answer. This is me kind of, you know, putting some thoughts down to guide your thinking. It's up to you, the student, to come up with a statement and an explanation. Put those ideas together. Let me reiterate it one more time for everybody's benefit. Because we've increased the variable resistor here, these are fixed resistors, right? We're not changing them. So if we increase this, then the circuit resistance or the combined resistance increases. Because we've increased the circuit resistance, less current is going to be drawn from the batteries. And because there's less current, there's less power. Okay. So again, don't just, if you were to write these symbols on your paper and submit it, you would earn 0 out of 3 marks. Right? That's not an explanation. This is just equations. So you do need to kind of, you know, draft a good sentence there that captures those ideas. And go ahead and leave it down in the comments below. This has been another worked example with Dr. Schleif. We'll see you next time.